Tonight, we're going to talk about an object that shouldn't exist. A dead star spinning 707 times every single second. That's faster than a jet engine, faster than a bullet, so fast that if it spun just slightly faster, it would literally rip itself apart. And right now, as we speak, it's slowly destroying another star, tearing it to pieces with radiation so intense that NASA has dedicated instruments to watching this cosmic destruction play out in real time. They call it a black widow pulsar, and by the end of tonight, you're going to understand why this one object is forcing physicists to question everything they thought they knew about the limits of reality. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what we're actually looking at here. Pulsar J0952-0607. That's its official designation, though scientists sometimes just call it J0952 for short. The name tells you something immediately. The J means it was discovered relatively recently using modern survey techniques. The numbers 0952-0607 tell you its coordinates in the sky. Right ascension, 9 hours 52 minutes. Declination, -0 degrees, 6 arc minutes, 7 arc seconds. It sits in the constellation Sextans, not one of the famous constellations, but visible from the southern hemisphere. It's approximately 3,800 light-years from Earth. That light you'd see if you pointed a powerful enough telescope at it left that object 3,800 years ago, when the pyramids of Egypt were already ancient monuments and human civilization was just beginning to develop writing. But here's what makes this object absolutely extraordinary. Pulsar J0952 is spinning 707 times per second. Let me say that again so you fully understand what that means. 707 complete rotations every single second, not per minute, not per hour, per second. This is an object about 20 kilometers across, roughly the size of a small city, with more mass than our entire sun, rotating at a speed that seems physically impossible. The surface of this object is moving at approximately 15% of the speed of light. 15%. If you were somehow standing on the surface, which you absolutely could not do for reasons we'll get into, you'd be moving at about 45,000 kilometers per second. For comparison, Earth rotates once every 24 hours. Our sun rotates once every 27 days at its equator. Even the fastest spinning stars we know of, young massive stars, rotate maybe once every few hours at most. 707 rotations per second is beyond extreme. It's approaching the theoretical limit of how fast anything can possibly spin before it tears itself apart. And yet, this object has been spinning at this rate for millions of years. This isn't a star in any normal sense. It's a pulsar, which means it's a neutron star, and neutron stars are among the strangest objects in the universe. To understand what makes J0952 so dangerous, we need to understand what a neutron star actually is and how it came to exist. Neutron stars are the collapsed cores of massive stars that exploded as supernovae. When a star much more massive than our Sun, typically at least 8 to 10 times the Sun's mass, reaches the end of its life, it runs out of fuel. For millions or billions of years, the star has been fusing lighter elements into heavier ones in its core. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. Carbon and oxygen fuse into heavier elements like neon, magnesium, silicon. Each fusion reaction releases energy that creates an outward pressure, holding the star up against the crushing inward pull of its own gravity. But fusion can only proceed up to iron. Iron is the most stable nucleus. Fusing iron into heavier elements doesn't release energy. It requires energy input. So when a massive star's core fills with iron, fusion stops. Suddenly, there's no outward pressure to hold the star up. Gravity wins. The core collapses. In less than 1 second, a core roughly the size of Earth, containing more mass than our entire Sun, collapses down to a sphere only about 20 kilometers across. The collapse happens so fast and releases so much gravitational energy that the outer layers of the star rebound and explode outward. This is a supernova, one of the most energetic events in the universe. For a few weeks, the exploding star can briefly outshine an entire galaxy of hundreds of billions of stars, but we're interested in what's left behind in the core. After the explosion, after the outer layers have been blown into space, what remains is a neutron star. A sphere about 20 kilometers in diameter containing between 1.4 and about 2 solar masses. To understand how dense this is, imagine taking our entire Sun, which is 1.4 million kilometers in diameter, and crushing it down to the size of a city. A teaspoon of neutron star material would weigh about 1 billion tons. That's roughly the mass of Mount Everest, compressed into a volume you could hold in your hand. The density is approximately 100 trillion times the density of water, or about 1 billion times the density of lead. At these densities, atomic structure as we know it breaks down completely. In normal matter, atoms are mostly empty space. The nucleus is tiny, surrounded by a cloud of electrons orbiting at relatively large distances. But in a neutron star, the pressure is so extreme that electrons are forced into the nuclei, combining with protons to form neutrons. The neutron star is essentially one giant atomic nucleus held together by its own gravity. The surface of a neutron star is solid, crystalline iron, compressed to densities millions of times greater than normal iron. Below the surface, deeper into the star, matter exists in forms that can't be recreated in any laboratory on Earth. Exotic states of matter where individual neutrons are packed so tightly they begin to overlap. At the very center, in the core, conditions might be so extreme that neutrons break down into their constituent quarks, creating what physicists call quark matter. We're not entirely sure what happens at the absolute center, because we can't create these conditions experimentally, and our theories of nuclear physics begin to break down at these densities. Gravity on the surface of a neutron star is about 200 billion times stronger than gravity on Earth. If you could somehow stand on a neutron star, which you absolutely could not, you would instantly be flattened into a layer less than 1 atom thick. Any object falling onto a neutron star accelerates to approximately half the speed of light before impact. When it hits, the kinetic energy released is enormous, roughly equivalent to thousands of nuclear bombs per kilogram of material. Light itself struggles to escape from the surface. Photons climbing out of the gravitational well lose energy, their wavelength stretching, their color shifting toward red. This gravitational redshift can be as much as 30%. A photon that starts out as blue light at the surface emerges into space as red light. Now here's where pulsars come in. Not all neutron stars are pulsars, but many are. The word pulsar is short for pulsating star, though that's a misleading name. Pulsars don't actually pulsate or change their brightness. What they do is emit beams of electromagnetic radiation from their magnetic poles, and as the neutron star rotates, these beams sweep through space like lighthouse beams. If one of those beams happens to point toward Earth, we see a pulse of radio waves, or sometimes X-rays or gamma rays, every time the beam sweeps past us. The pulses are incredibly regular as the best atomic clocks humans have ever built. Some pulsars are so regular that they lose or gain less than 1 second over millions of years. This regularity is what makes pulsars useful as cosmic clocks and navigation beacons. But J0952 isn't just any pulsar. It belongs to a special category called millisecond pulsars because their rotation periods are measured in milliseconds rather than seconds. Most pulsars rotate relatively slowly by neutron star standards. Typical rotation periods are around 1 second. The very first pulsar, discovered in 1967, had a period of 1.33 seconds. But millisecond pulsars spin much faster. J0952 has a period of 1.4 milliseconds. One rotation takes 0.0014 seconds, 707 rotations per second. This raises an obvious question. How do neutron stars end up spinning so fast? When a massive star's core collapses to form a neutron star, it naturally spins relatively quickly because of conservation of angular momentum. Just like a figure skater pulling in their arms spins faster, a collapsing stellar core spins up as it shrinks. A star that was rotating once every few days might end up as a neutron star, rotating once per second after the collapse, concentrates all that angular momentum into a much smaller object, but that only gets you to rotation periods of roughly 1 second, not 1 millisecond. To spin 700 times per second requires something else. The answer is accretion, material falling onto the neutron star from a companion star in a binary system. This is where things get interesting, and where the Black Widow name comes from. Pulsar J0952 is not alone. It has a companion star orbiting around it. But this isn't a normal binary system where two stars orbit each other peacefully. This is a system where one star, the neutron star, is actively destroying the other. The companion star in this system is a small, low-mass star, probably only about 0.02 times the mass of our Sun. For comparison, our Sun has a mass of about 2 times 10 to the 30th power kilograms. The companion is only about 4 times 10 to the 28th power kilograms, roughly 20 times the mass of Jupiter. It's barely massive enough to be called a star at all. The orbital period is incredibly short. The two objects orbit their common center of mass once every 6.4 hours. They're extraordinarily close together, separated by a distance less than the distance from Earth to our Moon. And here's what's happening. The neutron star is slowly tearing its companion apart. The intense radiation from the pulsar, the powerful magnetic field, the tidal forces from gravity, all of these are stripping material from the surface of the companion star. Gas is being pulled away and either falling onto the neutron star or being blown out into space by the pulsar's wind. Over millions of years, the companion star is being evaporated, destroyed, consumed by the pulsar. This is exactly what a black widow spider does to its mate. The female black widow spider is much larger and more powerful than the male. After mating, she often kills and consumes the male. In the case of Pulsar J0952, the neutron star is the black widow, and its companion is the victim being slowly eaten. This process of destroying the companion is not just violent, it's essential to understanding why the pulsar spins so fast. Here's how it works. The companion star is so close to the neutron star that material from the companion's outer layers gets pulled toward the neutron star by gravity. This material doesn't fall directly onto the neutron star. Instead, because both objects are rotating and orbiting, the material forms an accretion disk, a flat disk of gas spiraling inward toward the neutron star. As material in the accretion disk spirals inward, it carries angular momentum. When it finally reaches the surface of the neutron star and gets accreted, incorporated into the neutron star, it transfers that angular momentum to the neutron star. This spins up the neutron star, making it rotate faster and faster. over millions or tens of millions of years. This process can take a neutron star that was originally rotating once per second and spin it up to hundreds of rotations per second. The neutron star essentially steals rotation from the companion star's orbit and converts it into its own spin. This is how millisecond pulsars form. They're old neutron stars that have been spun up by accretion from a companion. Without the companion, they'd have slowed down over time as they emit electromagnetic radiation and lose energy. But with a companion feeding them material, they get spun up to incredible speeds. Now, J0952 is not just any millisecond pulsar, it holds a very special distinction. As of the most recent measurements, it is the fastest spinning neutron star ever discovered, where we can accurately measure the mass. 707 rotations per second. There are a handful of pulsars that might be spinning slightly faster, but their measurements are less certain, or they don't have well-characterized companion stars that allow us to measure their masses. J0952 is the record holder. This immediately tells us something profound about the nature of matter. The fact that this object can spin 707 times per second without flying apart tells us that neutron star material is incredibly strong. Think about what's happening. The surface of the neutron star is moving at about 15% of the speed of light. At this speed, centrifugal force is trying to tear the star apart. The equator of the neutron star is bulging outward, trying to fling material into space. The only thing holding it together is the crushing inward pull of gravity and the structural strength of neutron star matter. For the neutron star to remain intact, the material must be strong enough to resist being ripped apart by these enormous forces. This tells physicists something about the equation of state of neutron star matter, a mathematical description of how matter behaves at nuclear densities. The faster a neutron star can spin without breaking apart, the stiffer the equation of state must be. By measuring the maximum rotation rate of neutron stars, we're essentially measuring the fundamental properties of matter under the most extreme conditions in the universe. But there's a limit. Theory tells us there's a maximum speed at which a neutron star can possibly rotate before it must fly apart, no matter how strong the material is. This maximum depends on the neutron star's mass and radius, but it's typically somewhere around 1,000 to 1,500 rotations per second. J0952 at 707 rotations per second is approaching this limit. It's not at the absolute maximum, but it's getting close. This raises fascinating questions. Why hasn't it been spun up even faster? Is there something limiting how fast accretion can spin up a neutron star? Or has the companion simply not provided enough material yet? One possibility is that there's a natural braking mechanism that prevents neutron stars from spinning up beyond a certain point. As the neutron star spins faster, its magnetic field becomes more and more powerful in the surrounding space. At some point, the magnetic field might become strong enough to push away incoming material, preventing further accretion and further spin-up. This would create a natural maximum rotation rate determined by the balance between gravitational attraction pulling material in and magnetic pressure pushing it away. Another possibility is that gravitational wave emission becomes important at very high rotation rates. If a neutron star is not perfectly symmetrical, if it has even a tiny mountain or bump on its surface, then, as it rotates, it emits gravitational waves. These waves carry energy away, slowing the neutron star down. At rotation rates approaching 1,000 per second, gravitational wave emission might be significant enough to prevent further spin-up. This is one reason why astronomers are interested in searching for gravitational waves from rapidly rotating neutron stars. Detecting such waves would tell us about the structure of the neutron star's surface and its interior. Now let's talk about the magnetic field, because this is where things get truly extreme. Neutron stars have the strongest magnetic fields of any object in the universe, except possibly magnetars, which are a special class of neutron stars with even more extreme magnetic fields. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's magnetic field. J0952, as a millisecond pulsar, probably has a somewhat weaker field than that, maybe around 100 billion times Earth's field, because the accretion process that spun it up also tends to reduce the magnetic field strength, but even 100 billion times Earth's field is still incomprehensibly strong. To put this in perspective, the strongest magnetic field ever created in a laboratory on Earth, sustained for more than a fraction of a second, is about 45 Tesla. Earth's magnetic field at the surface is about 0.00005 Tesla. A neutron star's magnetic field at its surface is about 100 million to 1 trillion Tesla. At these field strengths, the physics of matter changes completely. Atoms can't exist in their normal form. The magnetic field is so strong, it distorts the electron clouds around nuclei, stretching atoms into cigar shapes thousands of times longer than they are wide. Photons, particles of light, can split into multiple photons or combine with each other in the presence of such strong fields. Even the vacuum of space behaves strangely, becoming birefringent, meaning light traveling through it splits into two different polarization states that travel at slightly different speeds. If you could somehow observe the space around a neutron star with your naked eyes, which you absolutely could not for about 17 different reasons, you would see visual effects that have no analog in everyday experience. Light would bend in strange ways. Colors would shift and split. The vacuum would shimmer and ripple. The magnetic field also creates the beams of radiation that make pulsars visible. Charged particles, electrons and positrons, get trapped in the magnetic field and accelerated to extremely high energies. As they spiral along the magnetic field lines, they emit radiation. This radiation gets focused into tight beams that emerge from the magnetic poles of the neutron star. For reasons that aren't entirely clear, the magnetic poles are usually not aligned with the rotation axis. Just like Earth's magnetic North Pole is not exactly at the geographic North Pole, a neutron star's magnetic poles are typically tilted relative to its rotation axis. So as the neutron star rotates, the magnetic poles, and therefore the radiation beams, sweep around. If one of those beams happens to sweep across Earth, we see a pulse. The pulse we see from J0952 is not in the radio part of the spectrum, though many pulsars do emit radio waves. J0952 is primarily a gamma-ray pulsar. It emits most of its energy in gamma rays, the most energetic form of light, with photon energies millions of times higher than visible light photons. These gamma rays are produced by the most energetic particles in the pulsar's magnetosphere, electrons and positrons, accelerated to energies approaching the speed of light. This is one reason why NASA watches this pulsar so carefully. Gamma-ray observations require space-based telescopes because Earth's atmosphere blocks gamma rays. NASA's Fermi Gamma Ray Space Telescope, launched in 2008, has been observing J0952 and other gamma-ray pulsars for over a decade. The observations are not quite continuous, 24/7, as the title suggests, because the satellite has to observe many different targets and can't stare at one pulsar all the time. But J0952 is one of the highest priority targets and receives regular, frequent observations. Why? Because it's an ideal laboratory for studying extreme physics. The combination of rapid rotation, strong magnetic field, and high energy emission makes it perfect for testing theories of particle acceleration, magnetic field structure, and the behavior of matter under extreme conditions. Every observation teaches us something new. The pulse profile, the exact shape of how the gamma-ray brightness changes over one rotation, tells us about the geometry of the magnetic field and where the radiation is being emitted. The timing of the pulses, measured with incredible precision, tells us about the neutron star's rotation and how it's changing over time. Any glitches or sudden changes in rotation rate tell us about the interior structure of the neutron star and how the superfluid layers inside interact with the solid crust. But there's another reason J0952 is so scientifically valuable. It's one of the best systems we have for measuring the mass of a neutron star with high precision. This is crucial because neutron star masses are one of the main observables we can use to constrain the equation of state of matter at nuclear densities. In a binary system where one object is much more massive than the other, the orbital dynamics are dominated by the massive object. By carefully timing the pulses from J0952 over years of observation, astronomers can measure tiny variations in the pulse arrival times caused by the orbital motion of the pulsar around the system's center of mass. The pulsar is moving toward us for part of its orbit and away from us for another part. When it's moving toward us, the pulses arrive slightly earlier than expected because each pulse has less distance to travel than the previous one. When it's moving away, the pulses arrive slightly later. From these timing variations, you can determine the orbital period, the size of the orbit, the eccentricity, and ultimately the masses of both objects. The measurements for J0952 indicate that the neutron star has a mass of approximately 2.35 solar masses. This is important, very important. For a long time, theoretical models of neutron stars suggested they couldn't exceed about 2 solar masses. Above that mass, the degeneracy pressure of neutrons, the quantum mechanical effect that holds up a neutron star against gravity, would be insufficient. The star would collapse further, presumably becoming a black hole. But observations of several pulsars, including J0952, have shown that neutron stars can definitely exceed 2 solar masses. J0952 at 2.35 solar masses is one of the most massive neutron stars ever measured. There's another pulsar, J0348+0432, with a measured mass of about 2.14 solar masses, and yet another, PSR J0740+6620, which might be as massive as 2.8 solar masses, though that measurement is less certain. These massive neutron stars tell us that the equation of state must be stiff enough to support masses above 2 solar masses. This rules out some theoretical models of dense matter and constrains what can happen inside neutron stars. It tells us something about the fundamental forces between neutrons at nuclear densities. It might even tell us whether exotic matter like hyperons or strange quarks can exist in neutron star cores. If such exotic particles do form, they would soften the equation of state, making it harder for neutron stars to support high masses. The fact that we observe neutron stars above 2 solar masses suggests that either exotic matter doesn't form, or it forms but doesn't soften the equation of state as much as some models predicted. Now let's return to the Black Widow process, because this is where J0952 becomes actively dangerous to its companion. The pulsar is not just passively existing near its companion, it's actively irradiating it, heating it, and destroying it. The gamma-ray and X-ray emission from the pulsar is intense. When these high-energy photons hit the companion star, they deposit enormous amounts of energy into the star's outer layers. This heats the surface to temperatures of tens of thousands of degrees. For a star that would naturally have a surface temperature of maybe 3,000 degrees, this external heating is overwhelming. The heated material expands and becomes less gravitationally bound to the star. At the same time, The pulsar's magnetic field creates a powerful wind of charged particles streaming outward from the pulsar. This wind hits the companion star like a constant hurricane of high-energy particles. The combination of intense heating and particle bombardment blows material away from the companion's surface. Some of this material falls back onto the neutron star, continuing the accretion process. Some escapes the system entirely, lost to interstellar space. Over time, the companion star shrinks. It's losing mass, being evaporated by the pulsar it's orbiting. Current estimates suggest the companion in the J0952 system has a mass of only about 0.02 solar masses, or about 20 times Jupiter's mass. That's extremely low. For comparison, the smallest true stars, red dwarfs at the bottom of the main sequence, have masses around 0.08 solar masses. Below that, you get brown dwarfs, objects that never achieve sustained hydrogen fusion in their cores. The companion in J0952 is probably below even the brown dwarf limit. It's more like a giant planet being irradiated and destroyed by a pulsar than a proper star, and it's shrinking. Astronomers estimate that at the current rate of mass loss, the companion will be completely destroyed in another few 100 million to 1 billion years. The pulsar is eating its companion, slowly but inevitably. Eventually, all that will remain is a solitary millisecond pulsar, with no companion at all, spinning at 707 rotations per second, gradually slowing down over billions of years as it radiates energy. This process of companion destruction has been observed in several other Black Widow pulsar systems. There are now dozens of known Black Widow pulsars, and they all show similar characteristics. A rapidly spinning millisecond pulsar, a very low mass companion, a short orbital period, usually just a few hours, and evidence of ongoing mass loss from the companion. In some cases, astronomers can directly observe the material being blown off the companion star. It shows up as gas clouds in the orbit, visible in certain wavelengths. The gas is glowing because it's being heated by the pulsar's radiation. Some Black Widow systems show eclipses. As the companion star passes between us and the pulsar, it blocks some of the pulsar's emission. But the eclipse isn't caused by the star itself blocking our view. The star is too small to block much. Instead, the eclipse is caused by the cloud of gas surrounding the star, material that's been blown off the surface. This gas cloud is much larger than the star, and when it passes in front of the pulsar, it absorbs or scatters the pulsar's radiation, causing the pulses to fade or disappear. By studying how long the eclipses last and how deep they are, astronomers can estimate how much material is in the gas cloud and how fast it's moving. This gives us direct measurements of the mass loss rate from the companion. For J0952, the mass loss rate is estimated at roughly 10 to the power of -11 solar masses per year. That might sound like a small number, and in terms of stellar evolution, it is relatively slow, but over millions of years, it adds up. In 100 million years, the companion will lose about 10 to the power of -3 solar masses, or about 1 Jupiter mass. Since the companion's current total mass is only about 20 Jupiter masses, losing 1 Jupiter mass represents a significant fraction of its total mass. In a billion years, the companion could lose 10 Jupiter masses, roughly half its current mass. Eventually, perhaps in a few billion years, there will be nothing left. The companion will have been completely evaporated, consumed by the pulsar that once depended on it. This leads to an interesting question. What happens to the pulsar after the companion is gone? The pulsar itself will be fine. Neutron stars are incredibly stable objects. Once formed, they can persist for trillions of years, far longer than the current age of the universe. Without a companion to accrete from, the pulsar will simply continue spinning, gradually slowing down as it radiates energy. The slowdown is very gradual. A typical millisecond pulsar loses only a tiny fraction of its rotation rate over millions of years. At the current rate, J0952 will take billions of years to slow down to the point where it's no longer detectable as a pulsar. Eventually, far in the future, long after the Sun has died and Earth is gone, J0952 will become a slowly rotating, cold, dark neutron star, invisible to our telescopes, just another stellar corpse drifting through the galaxy. But that's billions of years away. Right now, it's one of the most active, violent, and fascinating objects in our corner of the galaxy. Let's talk about what it would be like to actually be near this object. Because understanding the environment around J0952 really drives home just how extreme it is. First, you could never get close. Long before you reach the neutron star itself, you'd be killed by radiation. The pulsar emits enormous amounts of high-energy gamma rays and X-rays. These would tear through any spacecraft, any spacesuit, any biological tissue. The radiation dose at a distance of, say, 10,000 kilometers from the pulsar would be lethal in seconds. At 1,000 kilometers, you'd receive a fatal dose in a fraction of a second. At 100 kilometers, the radiation flux would be so intense it would heat any material to thousands of degrees almost instantly. But let's imagine you had some magical, perfect radiation shielding and could somehow survive the radiation environment. What would you see? From a distance of, say, 100,000 kilometers, about 1/4 of the distance from Earth to the Moon, the neutron star would appear as a bright point of light. Not very impressive visually, because most of its emission is in wavelengths your eyes can't see. But if you could see in gamma rays, it would be one of the brightest objects in the sky, outshining everything except perhaps the companion star, which would also be very bright in X-rays due to being heated by the pulsar. As you moved closer, you'd start to see relativistic effects, because you'd need to be moving at a significant fraction of the speed of light to orbit safely at these distances without falling in, and because the neutron star's gravity warps space-time so severely, you'd see visual distortions. Light from the neutron star would be gravitationally lensed, bent around the star, allowing you to see parts of the surface that should be hidden behind the horizon. You'd see more than half the surface at once, because light from the backside would be bent around to reach you. The surface would appear distorted, stretched in strange ways. If you got close enough to see the surface, which would be impossible for many reasons, but let's imagine it anyway, you'd see a smooth, featureless sphere. The surface of a neutron star is probably perfectly smooth at large scales because gravity is so strong that even the tiniest irregularities would be crushed flat. There are no mountains or valleys. Any bump higher than a few millimeters would collapse under its own weight. The surface is probably made of crystalline iron, but at densities millions of times greater than normal iron, arranged in a lattice structure, held together by pressure rather than normal chemical bonds. You might see hot spots near the magnetic poles where the intense particle acceleration is heating the surface. These spots would be glowing in X-rays and gamma rays, invisible to your eyes but detectable with instruments. And you'd see the pulsar wind, the stream of charged particles flowing outward from the magnetic poles. This wind would be moving at close to the speed of light, glowing with synchrotron radiation as the particles spiral through the magnetic field. But here's the really strange part. Because the neutron star is spinning 707 times per second, all of these features would be rotating so fast you couldn't track them. The surface would appear as a blur. The hot spots would sweep past 700 times per second, far too fast for human perception. You'd see a flickering, but individual pulses would blend together. Only with high-speed cameras or instruments could you resolve the individual rotations. If you were in orbit around the neutron star at a relatively safe distance, say 10,000 kilometers, you'd complete one orbit in about 1 second. At 1,000 kilometers, you'd orbit in about 1/10 of a second. This is because orbital velocity depends on the mass of the object you're orbiting and how far you are from it. For a 2 solar mass neutron star, orbital velocity at 1,000 kilometers is roughly half the speed of light. At this speed, special relativistic effects become important. Time would pass slower for you than for someone far away from the neutron star. If you orbited at 1,000 kilometers for what seemed to you like 1 hour, when you escaped and traveled back to distant space, you'd find that several hours had passed there. You'd have aged less than people who stayed away from the neutron star. This is gravitational time dilation combined with velocity time dilation. Both effects work in the same direction near a neutron star, making time pass slower for you. Now let's consider the companion star. If you could safely observe from a distance, what would the interaction between the pulsar and its companion look like? The companion would appear as a small, dim, reddish object. It's only about 1/10 the radius of our Sun, and it's a cool, low-mass star or brown dwarf. Normally, it would be barely visible, too faint to see without a telescope. But in this system, the side facing the pulsar would be incredibly bright, heated to tens of thousands of degrees by the pulsar's radiation. This side would glow brilliant blue-white. The other side, the night side, would remain cool and reddish. The companion would look like a crescent, with one side blazingly bright and the other side dim. As it orbited, which takes only 6.4 hours, you'd see the bright side rotate in and out of view. The companion would also appear distorted, stretched toward the pulsar by tidal forces, and you'd see material streaming off the hot side, gas blown away by the pulsar wind and radiation pressure. This gas would glow as it heated up, creating a luminous tail or stream connecting the companion to the pulsar. Some of this gas would spiral inward toward the neutron star, forming a faint accretion disk. The disk would be relatively small because the accretion rate is now quite low, but it would be incredibly hot, glowing in X-rays. The entire system would be surrounded by a bubble or bow shock, where the pulsar wind slams into the thin gas of interstellar space. This shock front would be glowing faintly in radio waves and possibly X-rays, extending for light years around the pulsar. It's a violent, chaotic, beautiful, and deadly environment. Now here's something that doesn't get talked about enough. Let's step back for a moment and talk about how astronomers actually discovered this object, because the story of finding J0952 reveals a lot about modern astronomy and how we detect objects that are thousands of light years away. The discovery came from the Fermi Gamma Ray Space Telescope, a NASA mission that has been scanning the entire sky in gamma rays since 2008. Fermi doesn't work like an optical telescope. You can't just point it at a spot in the sky and take a picture. Instead, it has a wide field of view and constantly scans the sky, detecting high-energy photons as they arrive. Over weeks and months, it builds up a map of the gamma-ray sky. Most of the gamma-ray sources Fermi detects are continuous. They emit gamma rays steadily, without dramatic variation, but some sources show periodic variation. Their brightness pulses on and off with extraordinary regularity. These are pulsars. The challenge is finding them. When Fermi detects a pulsing gamma-ray source, it records the arrival time of each photon with microsecond precision. But to determine that the source is pulsing, you need to search the data for periodicity. This is computationally expensive. You have to search through many possible periods, many possible pulse shapes, accounting for the fact that the pulsar might be in a binary orbit, which would Doppler shift the pulses. For J0952, the period is only 1.4 milliseconds. That's 707 times per second. This makes the search even harder because you need very precise timing to resolve such rapid pulses. The initial detection came in 2017, when astronomers were systematically searching through Fermi data for millisecond pulsars. They noticed a source that showed periodic gamma-ray emission with a period of 1.4 milliseconds. This immediately flagged it as interesting. A period this short meant it had to be a millisecond pulsar, and millisecond pulsars are always scientifically valuable. But the real surprise came when they analyzed the timing data more carefully. The pulses showed periodic variations that indicated the pulsar was in a binary orbit. By measuring how the pulse arrival times varied over hours and days, they could determine the orbital period, 6.4 hours, extremely short. They could also determine that the pulsar was being eclipsed periodically, meaning material from the companion was passing between the pulsar and Earth, blocking the gamma-ray emission. These eclipses immediately identified the system as a black widow. Only black widow systems show eclipses, because only in these systems is there enough material being blown off the companion to create a dense enough cloud to block the pulsar's emission. Once the gamma-ray emission was detected and characterized, astronomers followed up with optical telescopes to look for the companion star. This is harder than it sounds. The companion is very faint because it's a low-mass star or brown dwarf, and it's being heavily irradiated by the pulsar, which makes it appear much brighter on one side than the other. But with careful observations using large telescopes, astronomers were able to detect the companion and measure its properties. They found it was indeed a very low-mass object, probably around 0.02 solar masses. They could see that it was being heated on one side, with temperatures reaching tens of thousands of degrees, and they could detect the orbital motion as the companion moved around the pulsar every 6.4 hours. From all this data, combined with theoretical models of how binary systems work, astronomers could calculate the mass of the pulsar. The result was 2.35 solar masses, making J0952 one of the most massive neutron stars ever measured. This discovery process represents modern astronomy at its best. Multiple wavelengths of observation, gamma rays to find the pulsar, optical light to find the companion, careful timing analysis to determine orbital parameters, theoretical modeling to interpret the observations, and international collaboration, with data from NASA's Fermi telescope being analyzed by astronomers around the world, followed up by ground-based telescopes, and ultimately published in scientific journals for the entire astronomical community to study. Now let's talk about how J0952 compares to other pulsars, because putting it in context really drives home how extreme it is. The very first pulsar ever discovered was found in 1967 by Jocelyn Bell Burnell, a graduate student working with Anthony Hewish at Cambridge University. She was using a radio telescope to study quasars when she noticed a strange signal, a radio source that pulsed on and off with a period of 1.33 seconds. The regularity was so precise that for a brief time, there was speculation it might be a signal from an alien civilization. They even nicknamed it LGM-1 for Little Green Men. But further observations found more pulsing radio sources, and the explanation became clear. These were rotating neutron stars, their radio beams sweeping across Earth like lighthouse beams. That first pulsar, now officially called PSRB 1919+21, has a period of 1.337 seconds. It rotates once every 1.337 seconds. Compare that to J0952's rotation of 707 times per second, and you see the difference. J0952 rotates more than 900 times faster. Most pulsars discovered over the next decade or so had similarly long periods, ranging from about 0.2 seconds to several seconds. This made sense based on the theory of how neutron stars form. When a stellar core collapses, conservation of angular momentum spins it up, but not to millisecond periods. You'd expect periods of roughly 1 second, which is exactly what was observed. Then, in 1982, astronomers discovered something completely unexpected, a pulsar with a period of just 1.55 milliseconds. 641 rotations per second. This was Pulsar J0952-0607, and its discovery changed everything. A period this short couldn't be explained by stellar collapse alone. The pulsar had to have been spun up by accretion from a companion star. This confirmed a theoretical prediction that had been made years earlier. Astronomers had proposed that old neutron stars in binary systems could be recycled by accreting material from their companions, spinning them up to millisecond periods. The discovery of Pulsar J0952-0607 proved this recycling process was real. Since then, hundreds of millisecond pulsars have been discovered. Most have periods between 1 and 10 milliseconds, corresponding to rotation rates of 100 to 1,000 times per second. J0952. At 1.4 milliseconds and 707 rotations per second, sits near the fast end of this distribution. It's not quite the absolute fastest pulsar ever detected. There are a few pulsars with reported periods slightly shorter than 1.4 milliseconds. For example, Pulsar J1748-2446e has a period of about 1.4 milliseconds as well, essentially tied with J0952. And there are claims of pulsars with periods as short as 1.1 milliseconds, though these measurements are less certain. But J0952 has a crucial advantage. We can accurately measure its mass because it has a companion star whose orbital motion allows us to weigh the system. Many of the other ultra-fast pulsars are isolated, with no companions, which makes measuring their masses much harder. So J0952 holds the record for the fastest spinning neutron star, where we can confidently determine the mass. This makes it scientifically more valuable than faster spinning pulsars, where the mass is uncertain. Comparing J0952 to other types of neutron stars also highlights how special it is. There are magnetars, neutron stars with magnetic fields even stronger than typical pulsars. Magnetars can have magnetic fields up to 10 to the 15th power Tesla, about 10,000 times stronger than typical neutron stars. These objects occasionally produce enormous bursts of X-rays and gamma rays when their magnetic fields suddenly reconfigure. A magnetar outburst can release more energy in 1/10 of a second than our Sun emits in 100,000 years. But magnetars rotate slowly, typically once every 5 to 10 seconds. Their strong magnetic fields cause rapid spin-down, slowing them much faster than regular pulsars. Then there are radio pulsars, the most common type, which emit most of their energy in radio waves rather than gamma rays or X-rays. These are typically slower, rotating pulsars with periods of 1 to several seconds. They're detectable out to large distances because radio waves can travel through the galaxy without being absorbed. There are anomalous X-ray pulsars, which are probably young neutron stars or magnetars that emit primarily in X-rays. And there are X-ray binary pulsars, neutron stars actively accreting from companion stars that emit bright X-ray emission as the accreted material crashes onto the neutron star surface. Each type of neutron star teaches us something different about extreme physics. But millisecond pulsars, especially black widows like J0952, are special because they combine several extreme properties: fast rotation, precise timing, active companion interaction, and the ability to measure masses accurately. Let's dive deeper into the physics of neutron star structure because understanding what J0952 is made of helps explain why it can spin so fast without flying apart. The interior of a neutron star is divided into several distinct layers, each with different physical properties. At the surface, you have the crust. This is solid, probably made of iron nuclei, arranged in a crystalline lattice, but compressed to densities millions of times greater than normal matter. In normal iron, atoms are separated by distances much larger than the nuclei themselves. In neutron star crust material, the nuclei are packed much more tightly. The crust extends down to a depth of about 1 to 2 kilometers. As you go deeper, the density increases and the nuclei become more neutron-rich. Normal iron has 26 protons and about 30 neutrons. In the neutron star crust, you might have nuclei with 26 protons but hundreds of neutrons. These are nuclei that cannot exist anywhere else in the universe except inside neutron stars. Below the crust, you reach the outer core. Here, the density is so high that atomic nuclei can no longer maintain their individuality. They merge together into a uniform fluid of neutrons, protons, and electrons. This is called neutron matter, and it behaves in ways that are completely unlike any normal fluid. It's a degenerate fluid, meaning quantum mechanical effects dominate. The neutrons are packed so tightly that they occupy essentially all available quantum states up to a certain energy level. This degeneracy pressure is what holds up the neutron star against gravity. It's not like the pressure in air or water, which comes from particles bouncing around thermally. It's a purely quantum mechanical effect, arising from the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state. The outer core probably extends from about 1 to 2 kilometers depth down to about 8 to 10 kilometers depth. Below that, you reach the inner core, and here things get really uncertain. At the densities in the inner core, normal neutrons might not be able to exist. The pressure might be so high that neutrons break down into their constituent quarks. Neutrons are made of 3 quarks, 2 down quarks, and 1 up quark, held together by the strong nuclear force. At normal densities, quarks are always confined inside particles like protons and neutrons. They never exist freely. But at the extreme densities in neutron star cores, it's possible that quarks become deconfined, forming a quark matter state, where quarks move freely rather than being bound inside individual neutrons. This would be called a quark-gluon plasma, or strange quark matter, depending on exactly what happens. Another possibility is that hyperons form. Hyperons are particles, like lambda particles or sigma particles, that contain strange quarks. At normal densities, hyperons are unstable and decay rapidly. But at neutron star core densities, hyperons might be stable and could make up a significant fraction of the matter, or there might be other exotic particles we haven't even thought of, pions or kaons. Particles normally seen only in high-energy particle physics experiments might exist in stable form in neutron star cores. We simply don't know. The problem is that we cannot recreate these conditions in laboratories. The highest densities we can achieve in particle colliders or with compression experiments are far below neutron star core densities. So we have to rely on theoretical extrapolations of nuclear physics into regimes we've never directly tested. This is where observations of objects like J0952 become crucial. The maximum rotation rate a neutron star can sustain depends on its equation of state, the mathematical relationship between pressure and density for matter at nuclear densities. If the equation of state is stiff, meaning pressure increases rapidly with density, then the neutron star can resist deformation and can spin faster before centrifugal forces tear it apart. If the equation of state is soft, meaning pressure increases slowly with density, then the neutron star is more easily deformed and cannot spin as fast. The fact that J0952 is spinning at 707 times per second tells us the equation of state must be stiff enough to support this rotation rate. Similarly, the fact that J0952 has a mass of 2.35 solar masses tells us the equation of state must be stiff enough to support that much mass. If the equation of state were too soft, a neutron star couldn't reach 2.35 solar masses before collapsing into a black hole. By combining measurements of rotation rates and masses from many different neutron stars, astronomers and physicists can constrain the equation of state. Different theoretical models of neutron star matter predict different maximum masses and maximum rotation rates. By comparing these predictions to observations, we can rule out models that don't match reality. This is how astronomy contributes to nuclear physics. We're using neutron stars as laboratories to study matter at densities we cannot achieve any other way. Let's talk more about the magnetic field and how it creates the pulsar wind. The magnetic field of a neutron star is not just strong, it's geometrically complex. The field has a dipole structure, roughly like a bar magnet, with magnetic field lines emerging from one pole and returning at the other pole. But the magnetic poles are not aligned with the rotation axis. In most pulsars, the magnetic axis is tilted relative to the rotation axis by tens of degrees. As the neutron star rotates, the magnetic field rotates with it. This rotating magnetic field creates an electric field in the surrounding space. Charged particles, electrons and positrons, get accelerated by this electric field to extremely high energies. These particles stream outward along the magnetic field lines, creating the pulsar wind. The pulsar wind is not like wind on Earth, made of slow-moving air molecules. It's a relativistic wind, with particles moving at speeds very close to the speed of light. These particles carry enormous amounts of energy away from the neutron star. For J0952, the spin-down power, the rate at which the pulsar is losing rotational energy, is approximately 2.5 times 10 to the power of 35 watts. That's 2.5 followed by 35 zeros watts. To put that in perspective, that's about 60,000 times the total power output of our Sun in all wavelengths combined. And this energy is not being emitted as gentle light. It's being emitted as relativistic particles and high-energy gamma rays. When these particles and photons hit the companion star, they deposit enormous amounts of energy into its surface. The companion's surface temperature on the side facing the pulsar reaches tens of thousands of degrees, far higher than the star's natural surface temperature. This heating drives the evaporation process that's destroying the companion. The magnetic field also determines where the radiation is emitted. The beams of gamma rays that we see from J0952 are coming from regions near the magnetic poles. Exactly where is still debated. It might be from gaps in the magnetosphere, where the electric field accelerates particles. It might be from the outer magnetosphere, where the magnetic field structure becomes complex and particles can radiate efficiently. But wherever it comes from, it's focused into narrow beams that sweep across the sky as the neutron star rotates. We only see the pulsar because one of these beams happens to point toward Earth. If the beams pointed in different directions, we'd never know J0952 exists. It would be invisible to us, even though it's just as active and extreme. This means that for every pulsar we detect, there are probably several others oriented, so their beams miss Earth. The true number of millisecond pulsars in the galaxy is probably several times larger than the number we've detected. Now, let's discuss the orbital dynamics in more detail, because the interaction between J0952 and its companion is not just about radiation and evaporation. Gravity plays a crucial role too. The two objects orbit their common center of mass once every 6.4 hours. Because the neutron star is much more massive than the companion, about 100 times more massive, the center of mass is very close to the neutron star, but not exactly at its center. Both objects are actually orbiting a point in space that sits slightly outside the neutron star's surface. As they orbit, several effects come into play. First, there's tidal distortion. The companion star is not perfectly spherical. The side facing the neutron star is pulled more strongly by gravity than the far side, so the star gets stretched into an ellipsoidal shape, like an egg with one end pointing toward the neutron star. This tidal bulge is constantly moving as the companion rotates, which it does synchronously with the orbit. The companion is tidally locked, meaning it always shows the same face to the pulsar, just like our moon always shows the same face to Earth. The tidal distortion dissipates energy, heating the companion's interior and making it slightly easier for material to escape. Second, there's mass transfer and orbital evolution. As the companion loses mass, the total mass of the system decreases. This changes the orbital dynamics. When mass is lost from a binary system, the orbit can either shrink or expand, depending on how the mass is lost and where it goes. For J0952, the orbit is probably slowly widening as material escapes the system. But the effect is small, and it happens over millions of years, so the orbital period change is very gradual. Third, there are relativistic effects. At the orbital velocities in this system, which reach hundreds of kilometers per second, special relativity becomes marginally important. Time runs slightly slower for the objects when they're moving faster at closest approach, and general relativity predicts that the orbit should gradually lose energy by emitting gravitational waves. For J0952, the gravitational wave emission is extremely weak. The orbit is relatively wide by neutron star binary standards, and the companion is very low mass, so the system doesn't emit strong gravitational waves. The orbital decay from gravitational waves is far too small to measure with current technology, but in principle, it's happening. Over billions of years, if the companion weren't being evaporated, the orbit would very slowly shrink as gravitational waves carry away energy. For comparison, the Hulse-Taylor binary pulsar, which consists of two neutron stars in a much tighter orbit, loses enough energy to gravitational waves that the orbital period decreases measurably. Hulse and Taylor won the Nobel Prize for measuring this effect in the 1970s and 80s. But J0952's orbit is too wide for this effect to be detectable. The evaporation of the companion is happening much faster than gravitational wave-induced orbital decay. All of these orbital effects combine to create a complex dynamical system that evolves over time. Astronomers can model this evolution using computer simulations that incorporate all the relevant physics: gravity, mass transfer, evaporation, radiation pressure, magnetic fields, stellar structure. These simulations help us understand the past and future of the system. We can run simulations backward in time to figure out what the system looked like millions of years ago when the companion was more massive. And we can run simulations forward to predict what will happen millions of years in the future as the companion continues to shrink. These models suggest that J0952 is currently in a late stage of its Black Widow evolution. The companion has already lost most of its original mass and will be completely destroyed in another few hundred million to 1 billion years. After that, J0952 will become an isolated millisecond pulsar, spinning at hundreds of times per second with no companion. There are many isolated millisecond pulsars known. About half of all millisecond pulsars are isolated. Some of these might be former Black Widows that have already completely destroyed their companions. Others might have formed through different evolutionary paths. For example, some millisecond pulsars might have had white dwarf companions that were too massive and gravitationally bound to be destroyed. After the accretion phase ended, the white dwarf companion remained, and we see these as millisecond pulsar white dwarf binary systems. But some white dwarf companions might have been ejected from the system through complex three-body interactions if the system started with 3 stars. Or the white dwarf might have been destroyed in a later interaction. The diversity of millisecond pulsar systems we observe suggests that binary evolution can follow many different paths. J0952 represents one specific path, the Black Widow path, where the companion is actively being destroyed while we watch. This gives us a real-time view of binary evolution in action, something that's usually impossible in astronomy because most evolutionary processes take far longer than human lifetimes. Let's also discuss the discovery of systems like J0952 has completely changed our understanding of stellar evolution and binary interactions. For a long time, astronomers thought they understood how stars in binary systems evolve. 2 stars form together, they orbit each other, sometimes they exchange mass, sometimes one explodes and the other survives. But Black Widow pulsars revealed a completely new phase of binary evolution that nobody predicted. The idea that a neutron star could accrete enough material from a companion to spin up to millisecond periods was proposed in the 1970s and 80s. It explained why millisecond pulsars exist. They're old neutron stars that have been recycled by accretion. But the prediction was that after the accretion phase ended, you'd be left with a millisecond pulsar orbiting a white dwarf, the remnant of the companion star. And indeed, many millisecond pulsars do have white dwarf companions. But some, like J0952, have companions that are still being destroyed. The accretion hasn't ended. Instead, the pulsar is actively evaporating its companion, even while it continues to accrete from it. This was unexpected. It suggests that in some binary systems, the accretion process becomes destructive. The pulsar spins up to such high speeds and develops such a powerful magnetic field and wind that it starts destroying the companion faster than it can accrete from it. The companion shrinks. Eventually, it's reduced to a planet mass object, then eventually to nothing. This process creates a new evolutionary pathway. A binary system can evolve from a normal massive binary with 2 stars, through a supernova that creates a neutron star, through a phase of mass transfer that spins up the neutron star and creates a millisecond pulsar, then through a Black Widow phase where the companion is destroyed, ending finally with a solitary millisecond pulsar. This pathway was not in the textbooks 20 years ago. Now it's recognized as an important channel for creating isolated millisecond pulsars. Before we conclude, there's one more aspect of J0952 that deserves our attention, and that's what it teaches us about the sheer diversity of the universe. When you look up at the night sky with your naked eyes, you see perhaps a few thousand stars depending on how dark your location is. They all look roughly similar, just points of light of varying brightness. Some are slightly different colors if you look carefully, reddish or bluish, but fundamentally, they all seem like similar objects. Our sun seems like a typical star, and in many ways it is. But when you start studying stars in detail, you discover incredible diversity. There are red giants hundreds of times larger than the sun. There are white dwarfs smaller than Earth, but with the mass of the sun. There are blue supergiants thousands of times more luminous than the sun. There are brown dwarfs that never achieved fusion and barely qualify as stars. And then there are neutron stars, objects so extreme they seem impossible. A sphere 20 kilometers across, with twice the sun's mass, spinning hundreds of times per second, with magnetic fields trillions of times stronger than Earth's, slowly destroying a companion star while emitting beams of gamma rays that sweep across the galaxy. This isn't speculation or science fiction. It's real. It exists. And there are probably thousands of objects like it in our galaxy alone. The universe is far stranger than we imagined before we started studying it carefully. Every new type of object we discover expands our understanding of what's possible. Before the 1930s, nobody knew neutron stars could exist. The neutron itself was only discovered in 1932. Within a year, physicists realized that neutron stars might be possible, but they seemed too exotic to be real. Then in 1967, pulsars were discovered, and we realized neutron stars aren't just possible, they're common. Millions exist in our galaxy. Every massive star that explodes creates one. Then millisecond pulsars were discovered in the 1980s, showing that neutron stars could spin even faster than anyone expected. Then black widow pulsars were discovered in the 1980s and 90s, revealing this bizarre phenomenon of companion destruction. And each discovery expanded our sense of what's real, what's possible, what exists out there in the universe. J0952 is part of that expanding picture. It pushes the boundaries of what neutron stars can do. Fastest spinning with accurately measured mass. Most massive neutron stars ever observed. Clear evidence of active companion destruction. Perfect laboratory for testing extreme physics. Every superlative, every extreme property teaches us something, and here's something to think about. J0952 is 3,800 light-years away. That's relatively close by astronomical standards. It's in our own galaxy, in our cosmic neighborhood. But 3,800 light-years is still an enormous distance by human standards. If you could travel at the speed of the fastest spacecraft humanity has ever built, Voyager 1, at about 17 kilometers per second, it would take you about 70 million years to reach J0952. That's longer than the dinosaurs existed. We will never visit this object. We will never send a probe there. We will never see it up close with human eyes. Everything we know about it comes from photons that have traveled for 3,800 years to reach us. Light that left that neutron star when the pyramids of Egypt were already ancient structures and human civilization was just beginning to develop. And yet, from those photons, from careful observation and measurement and analysis, we can determine its mass to within a few percent. We can measure its rotation rate to extreme precision. We can infer its internal structure. We can predict its future evolution. We can understand the physics governing its behavior. This is the power of modern astronomy and physics. We can take light from remote objects and extract profound understanding from it. We can look at the universe and comprehend it in detail that would have been unimaginable to previous generations. Just 200 years ago, astronomers were still struggling to measure distances to the nearest stars. 100 years ago, we didn't even know other galaxies existed. We thought the Milky Way was the entire universe. 50 years ago, we'd only just discovered pulsars, and now we can study objects like J0952 in exquisite detail, understanding their internal structure, their evolution, their role in the cosmic ecosystem. The pace of progress is remarkable, and it shows no signs of slowing. In the coming decades, new telescopes and new technologies will reveal even more about neutron stars. We'll discover more examples of extreme objects. We'll measure properties with even greater precision. We'll test fundamental physics even more stringently, and we'll continue to expand the boundaries of human knowledge. That's the real story of J0952. It's not just one interesting object. It's a milestone in humanity's journey to understand the universe. It represents what we can achieve when we apply our intelligence, creativity, and persistence to understanding nature. And it points toward future discoveries we can barely imagine. Before this story ends, let's imagine one more scenario. Suppose you could somehow, magically, transport yourself to a safe observing distance from J0952. Maybe you're in a spaceship with perfect radiation shielding at a distance of 1 million kilometers. That's far enough to be relatively safe from the radiation, though still close enough to see the system clearly. What would you see? With optical telescopes, you'd see the companion star. It would look like a small, dim, reddish star, but one side, the side facing the pulsar, would be brilliant blue-white, heated to tens of thousands of degrees. As you watched, the companion would orbit the pulsar every 6.4 hours. You'd see the bright side rotate in and out of view, the star growing brighter and dimmer as different sides faced you. With X-ray detectors, you'd see the hot gas around the companion glowing intensely, and you'd see faint emission from near the neutron star, where material is being accreted. With gamma-ray detectors, you'd see the pulsar itself. 707 pulses every second, like a cosmic strobe light far more rapid than human eyes could perceive. You'd need high-speed cameras or instruments to resolve individual pulses. To your unaided perception, it would appear as a constant glow, flickering too fast to see as individual pulses. And all around, you'd see the bow shock where the pulsar wind meets the interstellar medium. A faint, glowing bubble extending for light years, invisible in optical light, but bright in radio and possibly X-rays. The entire scene would be beautiful in an alien, unsettling way. Not the gentle beauty of a sunset or a starry sky, but the harsh, extreme beauty of nature pushed to its limits. Colors that shouldn't exist together, blue-white next to deep red. Brightnesses that vary over timescales too rapid to follow with human senses. Radiation levels that would be instantly lethal without protection. It would be beautiful and deadly, fascinating and terrifying. And it would remind you that the universe contains environments utterly unlike anything in human experience. Places where the rules seem different, where matter behaves in ways that defy intuition. But the rules aren't different. The same physical laws that govern your spaceship govern the neutron star. The same equations of general relativity, the same quantum mechanics, the same thermodynamics. The laws are universal. It's just that at extreme conditions, those laws produce outcomes that seem impossible from our everyday perspective. This is one of the deepest lessons of studying objects like J0952. The universe operates according to consistent laws, but those laws allow for far more diversity, far more extremes, far more complexity than we could ever have imagined if we'd only studied our immediate environment. You need to study the entire universe, from the coldest voids to the hottest stellar cores, from the slowest rotating galaxies to the fastest spinning neutron stars, to fully appreciate what the laws of physics permit. And even then, you're probably only scratching the surface. There are probably types of objects and phenomena we haven't discovered yet. Configurations of matter and energy that are possible but rare or hard to detect. The universe is vast, and we've only studied a tiny fraction of it in detail. Every decade brings new surprises. 30 years ago, we didn't know dark energy existed. 25 years ago, we didn't know exoplanets were common. 15 years ago, we hadn't detected gravitational waves directly. 10 years ago, we hadn't imaged a black hole. 5 years ago, we hadn't detected the gravitational wave background. Each discovery changes our understanding. Each new observation reveals something unexpected. And objects like J0952 are part of that ongoing process of discovery and surprise. When it was first detected in 2017, it immediately became one of the most scientifically interesting objects in the sky. And as we continue to study it, it will undoubtedly reveal more surprises. Maybe we'll detect a glitch, a sudden change in rotation rate that tells us about the neutron star's interior. Maybe we'll see the companion change as it continues to shrink. Maybe we'll detect gravitational waves from the system if it has surface irregularities. Maybe we'll discover something completely unexpected that we hadn't even thought to look for. That's the nature of science. You study something because it seems interesting, and it teaches you things you didn't expect. You ask one question and end up answering a dozen others you hadn't even thought to ask. This is why basic research driven by curiosity rather than immediate practical applications, is so valuable. You never know what you'll discover. You never know what seemingly esoteric piece of knowledge will turn out to be important later. Understanding neutron stars seemed purely academic for decades. Now, neutron star collisions are recognized as the main source of heavy elements, like gold and platinum. Understanding pulsars seemed like an interesting curiosity. Now pulsar timing is being used to detect gravitational waves and potentially for spacecraft navigation. Understanding extreme physics seemed like a theoretical exercise. Now it's becoming relevant as we contemplate technologies that would have seemed impossible decades ago. The future is unpredictable, but one thing is certain. The knowledge we gain from studying objects like J0952 will be valuable, even if we can't predict exactly how. It will inform future theories. It will inspire future scientists. It will expand the boundaries of what humanity knows about reality. And that expansion of knowledge is one of our species' most important activities. It's what makes us distinctively human. Other animals survive and reproduce. Only humans ask why and how about everything we observe. Only humans build telescopes to observe remote objects. Only humans develop mathematical theories to explain what we see. Only humans create multi-generational projects to expand knowledge that won't pay off within our individual lifetimes. This long-term, collective accumulation of knowledge is civilization's greatest achievement. More important than any individual discovery is the process itself. The process of observing, measuring, hypothesizing, testing, refining, publishing, debating, and building toward ever deeper understanding. That process has been going on for centuries, and objects like J0952 are part of it. Each observation adds a data point. Each measurement constrains theoretical models. Each paper published becomes part of humanity's accumulated knowledge. And future generations will build on this knowledge just as we build on the knowledge of previous generations. Someone reading this decades from now will know things about J0952 that we don't know yet. They'll have observed it for longer. They'll have better instruments. They'll have more sophisticated theories. And they'll look back at our early observations the way we look back at 19th century astronomy, admiring what was achieved with limited tools while recognizing how much more there is to learn. That's the nature of science. It's never finished. There's always more to discover. Every answer raises new questions. Every mystery solved reveals new mysteries. And that's wonderful. It means there will always be work for curious minds to do. There will always be new frontiers to explore. The universe is vast enough, complex enough, that we'll never run out of things to study. J0952 is just one star in a galaxy of hundreds of billions of stars. One galaxy in a universe of trillions of galaxies. One object among countless billions of interesting objects scattered across the observable universe. And yet, studying this one object in detail teaches us about all the others. Every neutron star has something in common with J0952. Every Black Widow system can be understood better because we understand this one. Every millisecond pulsar is part of the same evolutionary story. The knowledge is transferable. It's cumulative. It builds on itself. And that's the power of scientific knowledge. You don't have to study every object individually. You study enough examples to understand the general principles, and then you can apply those principles broadly. You discover the laws governing neutron star behavior by studying dozens of examples. And then you understand all neutron stars, even ones you haven't observed. This is how science makes progress, despite the universe being too vast to study exhaustively. We find patterns, we discover laws, we build general theories, and then we test those theories against new observations. When they work, we become more confident. When they fail, we learn something new and revise the theories. This back and forth between theory and observation, between mathematical models and empirical data, is the engine that drives scientific progress. And it's been remarkably successful. Our current understanding of the universe, while incomplete, is vastly deeper and more accurate than any previous generation's understanding. We know things our ancestors couldn't have imagined knowing. We can calculate things that would have seemed like magic to people just centuries ago. And objects like J0952 are part of how we got here. Every observation contributed to the larger picture. Every measurement refined our theories. Every discovery expanded our knowledge. And the process continues. Thanks for joining me on this journey through the extreme universe. J0952, spinning impossibly fast, slowly consuming its companion, pushing physics to its limits, is one of the most remarkable objects we've ever discovered. It's not dangerous to us, but it's dangerous to ignorance, dangerous to complacency, dangerous to anyone who thinks the universe is simple or fully understood. It challenges us to think harder, to look more carefully, to understand more deeply. And in doing so, it makes us better scientists and better thinkers. The universe is full of wonders like this. Objects that seem impossible but are real. Phenomena that defy intuition but follow consistent laws. Mysteries that yield to careful observation and clear thinking. Every one of them is an invitation to learn, to discover, to understand. And that invitation is open to everyone willing to look up at the sky and ask questions. The same questions humans have been asking for thousands of years. What's out there? How does it work? Where did it come from? Where is it going? And what does it all mean? Those questions drive astronomy, drive science, drive human curiosity. And objects like J0952 help us answer them. One observation at a time. One discovery at a time. Building toward a complete understanding of everything that exists. That's the real story of this remarkable, impossible, wonderful object. A neutron star spinning 707 times per second, a cosmic black widow destroying its mate, a natural laboratory testing the limits of physics, a lighthouse in the dark, sending pulses across 3,800 light-years of space to tell us secrets about the universe. Keep looking up. The cosmos is full of objects like this, waiting to teach us. And every one of them is worth understanding. There's another aspect of J0952 that deserves attention, and that's what it tells us about the ultimate fate of matter in the universe. Every atom in your body, except for hydrogen, was created inside a star. Carbon, nitrogen, oxygen, iron, calcium, all the elements that make up your body and everything around you, were forged in stellar cores through nuclear fusion. When massive stars explode as supernovae, they scatter these elements into space. Later generations of stars and planets form from this enriched material. Our Sun is a third or fourth generation star, meaning it formed from material that had already been through multiple cycles of stellar birth and death. But neutron stars represent something different. They're the end point of one particular branch of stellar evolution, the fate of stars massive enough to explode as supernovae, but not massive enough to collapse into black holes. A neutron star can exist essentially forever. It doesn't undergo any further nuclear reactions. It doesn't evolve into anything else. It just sits there, slowly cooling, slowly spinning down, for trillions upon trillions of years. Eventually, in the unimaginably distant future, Long after all normal stars have burned out and the universe has gone dark, neutron stars will still be there. Cold, dark, slowly rotating corpses, remnants of stars that died billions or trillions of years earlier. In some sense, neutron stars are eternal. They're stable configurations of matter that, once formed, persist until the end of time. Unless they accrete enough material to exceed the maximum neutron star mass, in which case they collapse into black holes, or unless they merge with another neutron star or black hole, which destroys them and creates a black hole. But an isolated neutron star, left alone, will persist basically forever. J0952 will outlive our Sun, which will die in about 5 billion years. It will outlive the Milky Way galaxy, which will merge with Andromeda and eventually disperse as the universe expands. It will outlive every normal star in the universe, all of which will eventually exhaust their fuel and die. Trillions of years from now, the universe will be dark and cold, filled with black holes, neutron stars, and brown dwarfs. And J0952 will still be there, spinning slowly, invisible, cold, but still existing. This is both awe-inspiring and slightly melancholy. We're observing an object that will outlast everything we know, everything we can imagine. Our civilization, our planet, our sun, our galaxy as we know it, all of these are temporary. But J0952, this stellar corpse, this remnant of a violent death that happened millions of years ago, will persist essentially forever. Now let's return to the practical side of studying J0952 and talk about exactly how NASA and other observatories actually observe it and what they're looking for. The Fermi Gamma Ray Space Telescope has been the primary instrument for studying J0952. Fermi is in low Earth orbit, about 550 kilometers above Earth's surface. It carries two main instruments. The Large Area Telescope, or LAT, which detects gamma rays from 20 million electron volts up to more than 300 billion electron volts. And the Gamma Ray Burst Monitor, or GBM, which detects lower energy gamma rays and X-rays. For pulsar observations, the LAT is the primary instrument. It works by detecting gamma rays when they interact with layers of material inside the telescope. A gamma ray hits a thin sheet of tungsten and creates an electron-positron pair. These charged particles then pass through tracking detectors that record their paths. Below the trackers is a calorimeter that measures the particles' energies. From the tracks and energies, the telescope can reconstruct the direction the original gamma ray came from and how much energy it had. The LAT has a large field of view, about 20% of the entire sky at any given moment. As Fermi orbits Earth, the LAT scans across the sky, observing different regions. Over the course of about 3 hours, Fermi surveys the entire sky. This means every point in the sky, including J0952's location, is observed multiple times per day. For most sources, this scanning observation is sufficient. Fermi builds up a map of the gamma-ray sky, and scientists can analyze data from weeks or months of observations to study individual sources. But for pulsars, you need precise timing. You need to know exactly when each gamma-ray photon arrived, to within microseconds. This allows you to fold the data at the pulsar's rotation period and see the pulse profile. To achieve this timing precision, Fermi uses GPS receivers to timestamp every detected gamma ray. The timestamps are accurate to microseconds and are referenced to Coordinated Universal Time, the international time standard. When analyzing pulsar data, astronomers download all the gamma rays detected from the region of sky containing the pulsar. They then use sophisticated timing analysis software to search for periodicities in the arrival times. For J0952, With its 1.4 millisecond period, this requires extremely careful analysis. The data must be corrected for Earth's motion around the Sun, which Doppler shifts the pulses. If the pulsar is in a binary orbit, which J0952 is, the data must be corrected for the pulsar's orbital motion as well. Only after all these corrections are applied can you see the clear periodic signal. The result is a pulse profile, a graph showing how the gamma-ray intensity varies over one rotation period. For J0952, the pulse profile shows two main peaks per rotation, suggesting that we're seeing emission from both magnetic poles as they sweep past us. By studying how the pulse profile changes over time, astronomers can learn about changes in the pulsar's magnetosphere. By measuring tiny variations in the pulse arrival times, they can detect the orbital motion and determine the orbital parameters with extreme precision. This is called pulsar timing, and it's one of the most precise measurement techniques in all of astronomy. The best pulsar timing can measure pulse arrival times to within a few microseconds, even after accounting for all known effects. This precision allows astronomers to detect incredibly subtle effects. They can measure the gradual slowdown of the pulsar as it loses rotational energy. For J0952, the spin-down rate is about 3.5 times 10 to the power of -15 per second. That means the rotation rate is decreasing by about 3.5 femtohertz per second. This is an absurdly small number, but it's measurable with long-term timing observations. They can also detect glitches, sudden small increases in rotation rate that occur when the superfluid interior of the neutron star suddenly transfers angular momentum to the solid crust. J0952 hasn't shown any detected glitches yet, but many pulsars do, and timing observations are how we discover them. They can measure orbital parameter variations caused by mass loss from the companion or by relativistic effects. And in principle, though not yet achieved for J0952 specifically, they could detect gravitational waves passing through the solar system by looking for correlated timing variations in multiple pulsars. This timing precision is why pulsars are so valuable for fundamental physics. They're natural laboratories that we can monitor with extraordinary precision over years or decades. In addition to Fermi, other telescopes have observed J0952. Radio telescopes have searched for radio emission, though J0952 is primarily a gamma-ray pulsar and is weak or undetected in radio. Optical telescopes have observed the companion star, studying how its brightness varies as it orbits the pulsar and measuring its properties. X-ray telescopes like NASA's Chandra X-ray Observatory and ESA's XMM Newton have observed the system in X-rays, studying the hot gas around the companion and looking for X-ray emission from the pulsar itself or from an accretion disk. Each wavelength of observation reveals different aspects of the system. Gamma rays tell us about the highest energy processes in the pulsar magnetosphere. X-rays tell us about hot gas and possibly about accretion. Optical light tells us about the companion star. Radio waves, when detectable, tell us about lower energy processes in the magnetosphere and about the interstellar medium between the pulsar and Earth. By combining observations across all these wavelengths, astronomers build a comprehensive picture of what's happening in this extreme system. This multi-wavelength approach is fundamental to modern astrophysics. No single wavelength tells the complete story. You need to observe in multiple wavelengths to understand the full physical picture. Let's discuss some of the other Black Widow and Redback pulsar systems that have been discovered. Because J0952 is not alone. The first recognized Black Widow pulsar was PSRB 1957+20, discovered in 1988. It has a period of 1.6 milliseconds and a companion with a mass of only about 0.02 solar masses, similar to J0952's companion. Observations showed that the companion was being heated and evaporated by the pulsar, establishing the Black Widow phenomenon. Since then, dozens of Black Widow systems have been found. Each one has slightly different properties, teaching us about the diversity of these systems. Some have orbital periods as short as 90 minutes. Others have periods of several hours, like J0952. Some show deep eclipses, where the pulsar completely disappears for part of the orbit. Others show shallow eclipses or no eclipses at all. The companion masses range from as low as 0.01 solar masses, barely massive enough to be gravitationally bound, up to 0.05 solar masses or so. There's also a related category called redback pulsars. These are similar to Black Widows, but have more massive companions, typically 0.1 to 0.5 solar masses. The companions in redback systems are more substantial stars, and the systems are actively accreting, with material visibly flowing from the companion onto the neutron star. Redbacks might represent an earlier evolutionary stage, before the companion has been significantly evaporated, or they might represent a different evolutionary path, where the companion is massive enough to survive longer. The dividing line between Black Widows and redbacks is somewhat arbitrary, usually placed around 0.1 solar masses for the companion. But physically, they're related phenomena, both involving millisecond pulsars actively interacting with low-mass companions. One of the most extreme examples is Pulsar J0952-3430, which has one of the lowest mass companions ever detected, possibly less than 0.01 solar masses. The companion might be almost completely destroyed, reduced to a Jupiter mass object or less. Another interesting case is Pulsar J1718-3825, which has a very eccentric orbit. Most millisecond pulsar binaries have nearly circular orbits because tidal interactions and mass transfer tend to circularize orbits over time. But this system has an elliptical orbit, suggesting something unusual happened in its past. Maybe it underwent a recent phase of rapid mass transfer that perturbed the orbit. Or maybe it formed through a different mechanism, perhaps involving the disruption of a previous companion. Each of these systems is a puzzle, and by studying the ensemble of Black Widow and redback pulsars, astronomers are piecing together the full story of how these systems form and evolve. One fascinating question is whether Black Widow pulsars ever completely destroy their companions, or whether the companion always retains some minimum mass. If the companion is reduced to planetary masses, will the evaporation process stop because there's not enough mass left to generate significant evaporation? Or will the process continue until literally nothing is left? We don't know yet because we haven't observed a system through the entire destruction process. That would take millions of years. But by studying systems at different evolutionary stages, from redbacks with relatively massive companions, through typical Black Widows like J0952, to extreme cases with nearly destroyed companions, we can infer the evolutionary sequence. It appears that complete destruction is possible, and may be the ultimate fate of at least some of these systems. There's also the question of how common these systems are in the galaxy. We've discovered dozens of Black Widow and redback pulsars, but these are objects we can only detect if their beams point toward Earth, and if they're close enough and bright enough for our telescopes to detect. For every one we detect, there are probably several more oriented so their beams miss Earth. And there are probably many more at distances too great for us to detect with current instruments. Statistical studies suggest there might be several thousand Black Widow and redback pulsars in the Milky Way galaxy. That's a small fraction of the total pulsar population, which is estimated at around 100 million, but it's still a significant number. These systems represent an important phase in the life cycle of some binary star systems. They're not rare curiosities. They're a natural outcome of binary evolution for certain initial conditions. Let's return to the broader implications of studying neutron stars like J0952 for fundamental physics beyond just astrophysics. One of the deep questions in physics is whether our current theories, quantum mechanics and general relativity, are complete and correct, or whether they're approximations that break down under extreme conditions. Neutron stars are ideal places to test this. They have extreme gravity, so they test general relativity. They have matter at extreme densities, so they test quantum mechanics and nuclear physics. And they exist at conditions where both quantum effects and relativistic effects are important, which is the regime where we most expect our current theories might break down. So far, general relativity has passed every test. The orbit of binary pulsars matches predictions to extraordinary precision. The gravitational waves detected by LIGO match the waveforms predicted by general relativity. The timing of millisecond pulsars shows relativistic effects exactly as predicted. But there are alternative theories of gravity that make slightly different predictions. Some modified gravity theories predict that gravitational waves should travel at speeds slightly different from the speed of light. Some predict additional types of gravitational radiation beyond what general relativity allows. Some predict that the maximum mass of a neutron star should be different. By precisely measuring neutron star properties, we can test these alternative theories. The fact that we observe neutron stars with masses above 2 solar masses rules out some modified gravity theories that predicted lower maximum masses. The fact that gravitational waves from neutron star mergers arrived at almost exactly the same time as light from the same events, as observed in the 2017 neutron star merger, rules out modified gravity theories that predict different propagation speeds for gravity and light. These are powerful constraints. They don't prove that general relativity is exactly correct, but they severely limit how much any alternative theory can deviate from general relativity's predictions. On the quantum side, neutron stars test our understanding of the strong nuclear force, the force that holds atomic nuclei together. At normal densities, we have a good understanding of how the strong force works. Protons and neutrons are made of quarks, held together by particles called gluons that mediate the strong force. At low energies and densities, we can't calculate properties of nuclei directly from quark and gluon interactions because the math is too complicated. Instead, we use effective theories that describe how protons and neutrons interact with each other. These effective theories work well for normal nuclei, like those found in atoms on Earth. But at neutron star densities, we're pushing beyond the regime where these effective theories were tested and validated. We have to extrapolate, and different theoretical approaches give different predictions. Some approaches suggest that exotic particles like hyperons or kaons must form at high densities. Others suggest that quark matter forms. Still others suggest that neutrons remain the dominant constituent all the way up to black hole densities. Observations of neutron stars, particularly measurements of maximum masses and constraints on radii and rotation rates, help us distinguish between these possibilities. The existence of 2 solar mass neutron stars favors stiffer equations of state and disfavors some exotic matter scenarios. But there's still significant uncertainty, and observations of more neutron stars with different properties will continue to refine our understanding. In the long term, understanding neutron star matter might even have practical applications. Right now, it seems purely academic, but throughout history, understanding fundamental physics has eventually led to practical technologies. Understanding electromagnetism led to electric power and telecommunications. Understanding nuclear physics led to nuclear power and medical imaging. Understanding quantum mechanics led to transistors and computers. It's impossible to predict what technologies might eventually emerge from a complete understanding of matter at nuclear densities. But history suggests that fundamental knowledge eventually finds applications. Maybe someday, centuries or millennia from now, human civilization will have advanced enough to manipulate matter at nuclear densities or to engineer with neutron stars. It sounds like science fiction now, but so did splitting the atom or landing on the moon before the 20th century. For now, the value of studying neutron stars is primarily in expanding our fundamental understanding of the universe, and that has intrinsic value, independent of any practical applications. Humans have always wanted to understand how the universe works. It's part of what makes us human, the ability to look at a point of light in the sky and understand that it's a city-sized sphere of neutrons spinning 700 times per second is one of our species' greatest achievements. It required thousands of years of accumulated knowledge, from ancient astronomers tracking stellar motions, through Newton's laws of gravity and motion, through Einstein's relativity, through quantum mechanics, through nuclear physics, through astrophysics, through the development of telescopes and satellites and computers capable of analyzing vast amounts of data. Every generation built on the knowledge of previous generations, and the result is our current understanding, incomplete and imperfect but nonetheless profound. We can look at J0952 and understand not just that it exists, but why it exists, how it formed, what it's made of, what will happen to it in the future. That understanding is precious. It represents the collective intellectual achievement of our entire species, and it's still growing. Every observation of J0952, every paper published about it, every new pulsar discovered adds to our knowledge. We're living in an extraordinary time for astronomy. In the past few decades, we've discovered thousands of exoplanets, detected gravitational waves, imaged black holes, mapped the cosmic microwave background, discovered dark energy, identified black widow pulsars, and made countless other discoveries. The pace of progress is accelerating because our instruments keep getting better and our computational abilities keep increasing. In the next decade, new telescopes coming online will detect more pulsars, including more black widows and possibly even more extreme examples. The Square Kilometre Array, when completed, will be the world's largest radio telescope and will detect pulsars throughout the galaxy. Future gamma-ray missions will follow up on Fermi's discoveries with even greater sensitivity. Next-generation gravitational wave detectors will be able to see neutron star mergers across the entire universe. And all of this data will feed into increasingly sophisticated theoretical models that will help us understand neutron stars, and by extension fundamental physics, in ever greater detail. J0952 is not just an object we're studying, it's a key to unlocking deeper understanding of reality itself. Every photon that arrives from it carries information about conditions and processes we cannot recreate on Earth. Every timing measurement tells us something about gravity, about matter, about the evolution of stellar systems. And every year of observation adds to our knowledge, refining our models, testing our theories, pushing the boundaries of what we know. This is science at its best. Taking something utterly remote and extreme, something that seems to have no connection to everyday life, and extracting from it profound truths about how the universe works. The methods we use to study J0952, precision timing, multi-wavelength observation, theoretical modeling, computer simulation, these same methods apply across astrophysics. They're how we study everything from nearby planets to the most distant galaxies, and the knowledge we gain is cumulative. Understanding neutron stars helps us understand supernova explosions. Understanding supernovae helps us understand chemical evolution of galaxies. Understanding galaxy evolution helps us understand cosmic structure formation. Understanding cosmic structure helps us understand the Big Bang and the ultimate fate of the universe. It's all connected. J0952. This one remarkable object spinning impossibly fast while destroying its companion is part of a vast web of knowledge that encompasses the entire universe. When you look at it that way, even something as extreme and remote as a millisecond pulsar becomes personally relevant. It's part of the story of the universe, and we're part of that same story. The atoms in your body were created in stars. Some of those stars exploded as supernovae, possibly creating neutron stars. You and J0952 are made of the same fundamental stuff, forged in the same cosmic processes. The only difference is that J0952 represents matter pushed to its absolute limits, while you represent matter organized in one of the universe's most complex structures, a living, thinking being capable of understanding that connection. That's perhaps the deepest reason to care about objects like J0952. They remind us that the universe is one interconnected whole. We're not separate from it, observing from outside. We're part of it. Temporary arrangements of matter and energy that have become complex enough to ask questions about where we came from and where we're going. And objects like J0952 help us answer those questions, one observation at a time, one discovery at a time, building toward a complete understanding of everything that exists. That goal might be unreachable. The universe might be too vast and too complex for any finite intelligence to fully comprehend it. But the journey toward that understanding is one of humanity's greatest adventures. And every object we study, every mystery we solve, brings us one step closer. J0952 is one step on that journey. A spectacular, extreme, fascinating step that reveals truths about reality that would be invisible without it. So yes, NASA watches it, not continuously, but regularly, because it's incredibly valuable. Not dangerous to us, not threatening Earth in any way, but dangerous to simplistic views of physics, dangerous to incomplete theories, dangerous to anyone who thinks they understand the universe when they don't. It's an object that demands we expand our thinking, that forces us to confront just how extreme reality can be. And in doing so, it makes reality more wondrous, not less, more interesting, not less, more worthy of study and contemplation, not less. Two stars form together. They orbit each other. Sometimes they exchange mass. Sometimes one explodes and the other survives. The study of black widow pulsars has also taught us about particle acceleration in extreme magnetic fields. The process that creates the pulsar wind, that accelerates particles to nearly the speed of light, is not fully understood. We know it happens. We can observe the effects. But the detailed physics of how magnetic fields extract energy from a rotating neutron star and convert it into particle kinetic energy is still an area of active research. By studying systems like J0952, where we can observe the pulsar wind interacting with the companion star, we're learning about these processes. The wind is so powerful it can blow away material from a star. That tells us about its energy and momentum flux. The heating of the companion tells us about the radiation output. The eclipses tell us about the geometry of the wind and the gas clouds. All of this feeds into theoretical models of pulsar, magnetospheres, and particle acceleration. Another major area of research involves using millisecond pulsars for gravitational wave detection. This might seem like a strange connection, but it's actually incredibly important. Millisecond pulsars are nature's most stable clocks. Their rotation is so regular that we can predict the arrival time of pulses to within microseconds, even years in advance. Astronomers have been timing dozens of millisecond pulsars for decades, building up detailed models of each pulsar's position, rotation rate, and orbital parameters. Now here's the key insight. If a gravitational wave passes between Earth and a pulsar, it stretches and squeezes space-time along the path. This changes the distance the pulse has to travel, causing a tiny shift in the pulse arrival time. By carefully monitoring the pulse arrival times from many pulsars scattered across the sky, you can detect these shifts. If the same pattern of shifts appears in data from multiple pulsars, that's evidence for a gravitational wave passing through the solar system. This is called Pulsar Timing Array, and it's sensitive to gravitational waves with very long wavelengths and low frequencies, much lower than what LIGO can detect. LIGO detects gravitational waves with frequencies of tens to thousands of hertz, from events like black hole mergers that last only seconds. Pulsar timing arrays detect gravitational waves with frequencies of nanohertz, one cycle per few years, from events like supermassive black hole binaries that orbit each other for millions of years before merging. J0952 is not currently part of the main pulsar timing arrays because its orbital motion makes timing more complicated. But it's being studied carefully, because understanding its timing properties helps improve the overall technique. The better we understand how millisecond pulsars behave, the more confidently we can use them to detect gravitational waves. In fact, several pulsar timing array projects have recently reported evidence for a gravitational wave background, a sort of hum of gravitational waves coming from all directions in the universe, probably produced by thousands of supermassive black hole binaries in distant galaxies. This detection relied on years of precise timing of dozens of millisecond pulsars. It's one of the major astronomical discoveries of the past few years, and it wouldn't be possible without millisecond pulsars. So when we study J0952, we're not just learning about one weird object. We're learning about fundamental physics, about the limits of how fast matter can spin, about the behavior of matter at nuclear densities, about particle acceleration in extreme magnetic fields, about binary star evolution, about gravitational wave detection techniques. This one object, this cosmic lighthouse spinning 700 times per second while destroying its companion, is a laboratory for multiple branches of astrophysics. Let's talk about the future of this system. What will happen over the next million years, the next billion years? In the short term, over the next few million years, probably not much will change. The pulsar will continue spinning at roughly the same rate, slowing down imperceptibly. The companion will continue losing mass, shrinking slowly. The orbital period might change slightly as the companion's mass decreases. As the companion loses mass, the center of mass of the system shifts and the orbit adjusts. But these changes would be gradual, taking thousands or millions of years to become obvious. Over tens of millions of years, the companion will shrink noticeably. What is now a 20 Jupiter mass object might become a 10 Jupiter mass object. The mass loss rate might increase as the companion gets smaller and less gravitationally bound, or it might decrease if there's less material left to blow away. Over hundreds of millions of years, the companion could be reduced to just a few Jupiter masses. At this point, it would barely qualify as even a brown dwarf. It would be more like a hot Jupiter, a giant planet being irradiated by a pulsar. Eventually, in perhaps 1 to 2 billion years, the companion might be completely destroyed. All of its material will have been either accreted onto the neutron star or blown away into space. What remains will be a solitary millisecond pulsar, spinning rapidly with no companion. The pulsar will continue to slow down, but the process is very slow for millisecond pulsars. It will take billions of years for J0952 to slow down to the point where it's no longer detectable as a pulsar. The pulsar itself will remain a neutron star essentially forever. Neutron stars don't decay. They don't fuse material or undergo any active processes that would cause them to change fundamentally. They just cool down over time, radiating away their thermal energy. After trillions of years, far longer than the current age of the universe, J0952 will be a cold, dark neutron star with a temperature close to absolute zero, spinning perhaps once every few seconds, invisible and inert. But that's the far future. Right now, today, it's a spectacular object, a testament to the extremes that nature can produce. Let me give you some final context for just how remarkable this object is. In the entire Milky Way galaxy, there are probably a few 100 million neutron stars. Most are invisible, either too faint to detect or not oriented, so their beams point toward us. Of the neutron stars we can detect, most are regular pulsars with rotation periods of seconds. Only a few thousand are millisecond pulsars. And of those millisecond pulsars, only a few dozen are black widows actively destroying their companions. J0952 is not just rare, it's one of the most extreme examples of an already rare class of objects. It combines several extreme properties: fastest measured rotation for a well-characterized system, one of the highest measured neutron star masses, strong gamma-ray emission, active companion destruction. Each of these properties alone would make it interesting. Altogether, they make it unique. And that's why NASA and other space agencies dedicate telescope time to observing it. That's why astronomers write papers analyzing its properties. That's why it appears in scientific talks and conferences, because every observation teaches us something we couldn't learn any other way. You cannot create these conditions in a laboratory. You cannot simulate them perfectly on a computer. The only way to study matter at nuclear densities, spinning at 700 rotations per second in magnetic fields of 1 trillion Tesla, is to observe objects like J0952. Nature has provided us with this laboratory. We just have to point our telescopes at it and pay attention. Think about what this object represents. It's the compressed core of a star that died in a supernova explosion millions of years ago. That core collapsed down to a size smaller than a city but retained more mass than our entire sun. It's been spinning for millions of years, never slowing down noticeably, because conservation of angular momentum is absolute. It's been fed by a companion star, accreting material that spun it up to the edge of what's physically possible. And now it's destroying that companion, slowly, inexorably, over millions of years. In 1 billion years, the companion will be gone, and the pulsar will spin alone through the galaxy, a solitary testament to the violence of stellar death and the extremes of physics. Humans discovered this object only recently. The first millisecond pulsar was discovered in 1982. J0952 itself was discovered in 2017 using data from Fermi. We've only known about it for a few years. And yet, in that short time, it's taught us enormous amounts. That's the power of astronomy. We can observe objects billions of times older than human civilization, phenomena that play out over timescales far longer than our species has existed, and extract from them fundamental truths about how the universe works. We're part of the universe, trying to understand itself. And objects like J0952 are clues, pieces of evidence showing us what's possible, what's real, what happens when you push matter and energy to their limits. Every pulsar pulse that arrives at Earth carries information. It left the neutron star 3,800 years ago, traveled through interstellar space, survived passage through the galaxy's magnetic fields, and the solar wind entered Earth's atmosphere and struck a detector in a satellite. That photon's journey connects us directly to one of the most extreme objects in existence. When you understand what you're looking at, when you grasp what J0952 actually is, it becomes one of the most awe-inspiring objects in the universe. Not just because it's extreme, though it is. Not just because it's rare, though it is. But because its very existence demonstrates something profound about the nature of reality. The laws of physics allow objects like this to exist. Matter can be compressed to nuclear densities and remain stable. Objects can spin 700 times per second without flying apart. Magnetic fields can reach strengths that would vaporize normal matter. Gravity can be so strong that time itself slows down. And all of this happens, not in some theoretical model, not in some computer simulation, but in reality, 3,800 light-years away, right now. Tonight, as you look up at the sky, photons from J0952 are arriving at Earth. You can't see them with your eyes because they're gamma rays, but they're there. Every millisecond, 707 pulses arrive from a neutron star the size of a city with more mass than the Sun, spinning at 15% of the speed of light, slowly destroying its companion, being watched by instruments in space that humans built to study the extreme universe. That object is out there right now, behaving exactly as physics predicts it should, confirming our theories, challenging our understanding, existing at the edge of what's possible. And that's why it's so dangerous. Not dangerous to us directly, we're far too distant, but dangerous to its companion. Dangerous to our preconceptions about what's possible. Dangerous to any simple, intuitive understanding of how the universe works. Because the universe is far stranger, far more extreme, far more magnificent than everyday experience would suggest. J0952 is proof. Thanks for staying with me through this journey to one of the most extreme objects in our galaxy. The universe is full of wonders, and this cosmic black widow, spinning faster than seems possible while slowly consuming its mate, is one of the most spectacular. Keep looking up at those stars. They're not all quiet, peaceful points of light. Some of them are anything but peaceful. Some are violent, extreme, and absolutely fascinating. And every one of them has a story to tell if we're willing to listen.